Are they seeing the
what?
the screen or not?
I'm not sure.
But they no response from them.
Yeah. Okay, you're in. Okay, great. You share the screen?
Yeah.
What are you sharing?
So
Okay, what are you sharing? Sharing screen. Okay. Yeah, tablet. Like, yeah, okay, sure.
we didn't hit from the other side.
Yeah, okay.
It's okay.
Okay, okay.
We turn off light. Are we recording?
We're recording? I don't think so.
How do we start recording?
Okay, okay.
Yeah, not record.
Oh, cannot because China controls it.
China. Okay.
Yeah, because they didn't allow recording for this.
But should we wait response for them or we just start?
Start, huh?
Just start. Should we turn off light?
Oh. Yeah. Hello, so today we're going to begin our joint seminar. We're pleased to welcome Dr. Ngai Kiseng from Xiamen University, Malaysia. So he will talk about categorification, geometric representation theory from a link perspective. Okay, so we're very pleased to welcome Dr. Ngai for this talk.
Thank you for Darren for a wonderful introduction. Welcome everyone here. So I think there's the first time the students more than a professor here in the seminar. Okay. There's no one. Oh, good. It's good. Very good. In particular, there's some of my FYP students here. So hopefully you'll gain some insight after listening to the talk here. So today I'll talk about the subject on categorification. Basically, this is a geometric representation theory, but from the viewpoint of a link. Okay, from viewpoint of a link. So the reference for today was my paper that got published this year, coming from my PhD thesis, which I graduated 2 years ago. But the main idea is coming from Kovarnov and Seidel on these quiver flow homology and break group action. So mainly I'll talk about break group action. So feel free to stop me if you wish to. But basically, I will run through some concept. This talk kind of technical, but we won't go into much technicality here because there's no point to do it here. But if you are a person in this field, you can ask. Then maybe in my capacity, I can answer you. So basically, this talk breaks into 5 sections here. So first, I'll briefly mention about the origin of categorification. And then we'll start with an old problem in links. Hopefully everyone can understand this part here. Then we're going through the my main word in these faithful representations of break group. action. And finally, we try to link it back to link invariant and hopefully can explain some future work that can be done, maybe with the F5P or with a master student, or even if you are interested, we can go on PhD. So, I mean, we will spend most time in section 2 and 3, okay, and then quickly run through the other. So first of all, where does this categorification come from? So this word is coined in 1994. Okay, it's the same birth year as mine. By Crane and Frankel. Okay, this is with an A, for reinterpreting quantum mechanics in a general relativistic context. Okay, so actually these ideas came from physics. So this involved probing into the algebraic structure that govern the quantum theory of gravity, basically quantum gravity. So, so the conjecture was at that time. I'm not sure what happened now about this conjecture, but at that time the conjecture was quantum gravity is a two category which emerges as a categorization of the one category that formulate the Chen-Simon-Witten theory. It's okay that you don't know all these words, but I just want to give you an idea that there's a physics idea that we want to try and define properly, okay, in the context of category theory. Okay. Right, so roughly speaking, a categorification is of a mathematical object. P is replacing P with a higher structure mathematical object here. So for example, let me give you an example here. So for example, I will say that finite set categorify the natural number. Okay, so for example, if you take any finite set here, okay, and if you consider the cardinality of the finite set, it will be some natural number here. But finite set did better than natural number, because if you take two finite set, maybe you can consider some map between them. Okay, but if you just look at numbers, what you can do is you can talk about whether one number is smaller or greater than the other. But if you have a map between function, for example, a bijection, there's a lot of bijection between set with the same elements, right? So there are more possibility with this map instead of just less than or greater. Okay, so this is what we meant by a higher structure mathematical objects. So if you take cardinality, you will reduce to a less structured objects here. Make sense? Yeah. So later I will show you some instance of this kind of categorization where we replace a number or polynomial with maybe vector spaces. Vector spaces or modules, more generally. Okay. Right. So let's continue. So let's come to the knot. Okay. So basically I draw two knots here. One is the unknot, one is the trefoil knot. Okay, trefoil knot. So how do you create this knot? So every day you will tie your shoelaces, right? So you can get one of your shoelaces, okay, and you just make a tie around it. Number like this. And this is what we call a knot. Okay. But how to get this trefoil knot here? So imagine you tie it first, but you don't tie too tight first, and then you tie it again. Okay, let me finish. So if you have this knot with an extra tie here, and then you open it up, and this is the trefoil knot that I'm trying to draw there. Okay. So you can imagine that there's no way if you play around with this trefoil knot, you can unknot it. Okay, because at the beginning, I already tied a non-trivial knot into this shoelaces. Okay, so there's no way to do it unless you break it. Okay, so we are not trying to break it. We try to do it continuously. Okay, just by what we call isotopy, I will introduce later. Okay, without breaking it, can you make it into an unknown? Okay, so this is the problem we are interested in. So let's make this precise. So let's start with a knot. So what's a knot? A knot is an embedding of x1 into R3 or S3. So S1 is a circle. Okay, so basically S1 is a circle into R3, so three-dimensional space which we are living now, or S3. S3 is a three-dimensional sphere. Okay, so difference between S3 and R3 is S3 is compact. So we add an extra infinite point into it to compactify it. And how to talk about two knots to be equivalent? Okay, so we say that two knots are equivalent if there's an ambient isotopy here. So what does it mean by ambient isotopy? So this is a family of homeomorphism. So what's a homeomorphism is? Homeomorphisms are continuous bijective function. Okay, so the function have to be continuous, and then this function have to be bijective. Not only that, the inverse has to be continuous as well, right? So satisfy three properties here. So what are the three properties here? This family of homeomorphism go from time from 0 to 1 here. So in time 0, you really did nothing, okay, to the space. And throughout the time, you should do some continuous transform of this node, okay, until in the last second of time, you should reach your the other node, k prime, let's say. And if you consider this family of map here with an extra dimension time here, it should also define a homeomorphism also. Okay? It's also a homeomorphism with an extra time here. So it's basically R3 cross R. Okay, in R4 it's still a homeomorphism. Okay, so this is called the ambient isotopy. And what is R naught? So R naught is basically the boundary of an embedded disk. Okay, embedded disk. Right. So the problem is when is a knot and unknot. Okay, so this is generally phrased by a unknotting problem. So when is a knot and unknot? Actually, this is a topology problem. Okay, so in 1961, Hagen gave an algorithm to show that this question is decidable. Okay, using the theory of normal surfaces. But the algorithm is so complex, and that his paper is 130 pages long. So almost no one has put it into any practical use yet. Okay, so this is a topological approach here. So we try to solve it algebraically better. Okay, right. So there's no point to stop at knot. We can continue with links. So what's n link? So it's embedding of n disjoint x1 here. For example, I drew a two disjoint x1 here, so they can link together. And you can imagine there are few knots that you can link together as well to get n link. And all previous discussion can be extended, so you can talk about when the two links are the same. Okay, and you define what is unlinked. You define what is unlinked. So basically, you just put a bunch of circles without nothing. Right. So although our links are defined to sit in R3, really, what we just need to know is where's the crossing is. Correct? It doesn't matter whether this link is going far into the space. We just really care where the crossing is. Then we can recover this knot here. So basically, we can project it into R2 to draw. Okay. So to get this projection here, we need a regular projection. Okay. So only in this regular projection, only two strand intersections are allowed. Okay. So meaning whenever you make an intersection here, there's only two strand intersection. So you don't allow by a three strand intersection in your picture. And there are only finitely many of them. Okay. And also all the intersection must be traversal. So what does it mean by traversal here? So basically traversal, roughly speaking, is when you intersect, you can move them into a 90-degree configuration. Okay, so it won't like intersect tangentially like that. We don't allow something like this. Tangentially. So if you can see. So we don't allow tangential intersection. It should be moved away. this kind of, sorry? Yeah. So we don't allow tangential intersection. So the tangential intersection should be moved away. So only transversal intersection is allowed. So once you have these regular projection, you can consider the image of this projection. And you project R2 on the plane, and you can try and draw it out in R2. Okay, so basically what you care is about whether it is an undercrossing or overcrossing. So maybe let me draw something like this. So maybe you have this kind of crossing or the other kind of crossing. Okay, so this is a two crossing, the information you need in this link. Okay. Right. So here comes the randomizer theorem. So when does the two links are equivalent? So when we say that two links are equivalent if there is an ambient isotopy between them. But what we can do is we can do the projection and look at what's the link diagram. It turns out that there are equivalence between these two sets. Okay, obviously under some extra move here, which we call the randomizer move. Okay, so basically there are three randomizer move here. So first, you can straighten out the twisting. Okay, if you have a twist, you can just put it straight in R1. How about R2? Okay, so if you have two straight string, okay, you can bring them across. Okay. Then, or you can put it up.
Step on the camera.
Step on
the camera.
Okay, sorry. Sorry, let me bring my tool back. Okay. Right, so, yeah, the other guy need me. Okay. How about R3? So for R3, you can move your strand across any crossing. Okay, you can move your strand across any crossing. Move past the crossing. So basically, these are the isotopy that you need to care about, really. Okay, so this is what randomizer theorem tells you. Right, so how to study links? So one way to study links is through braid closure. I will define what is braid closure here. So to define braid, we will define what a geometric braid is. So we will define braid on n strands. Okay, so what's a braid of n strands? Basically, it's a set. Okay, so it's a subset of R2 cross the time interval 0 to 1. And what's this n strand about? This n strand is referring to the n disjoint topological intervals here. Okay, so you have a bunch of 0 to 1 intervals, and then you have costrands such that what? Such that the projection from R2 cross 1 to each I, okay, if you map each string homeomorphically onto I, okay, such that the endpoint is this set. So maybe if you're first time seeing this definition, you are sitting burnout. But let me draw you the picture here. So the picture is really easy to follow. So let's start with R2. Next one. Okay, and then we have an extra dimension here, but what we really care is just 0 to 1 for the moment. Okay, and the time is going from 0 to 1 here. For the braid. So what is an example of braid here? So let's draw 4-strand braid. So with 4-strand, for example, what we can do is, so we have these integer points, right? So 1, 2, 3 until n. So basically, we need to make 1, 3, 4 here. Here as well. And how do we draw this string? So we just make sure that it is a homeomorphism. Okay, so for example, we can draw something like this. So there's a crossing on the first strand and the second strand. And this strand, we will call it sigma 1. Strand 3 should be called sigma 1. So you can do random crossing. Okay, but I just give you an idea. So if you check at the endpoint, it should be 4 points. Okay, both endpoints, starting at time 0 and ending at time 1. It should be endpoint here. Okay, please.
Recording.
It's being recorded, yeah. I want to get the recording.
Okay.
Yeah.
Your B is 6 months, right? You use B your thing for 6 months.
My B is my sigma. Yeah, thank you. Yeah, sorry, I forget to change B's name. Yeah. Correction. This B is sigma. Thank you. Yes, that's right. I forgot to change. Yes. Thank you. Yeah, exactly. Okay. Right. Sure. So similarly, we can talk about when two strand is the same. Okay, when is two strand is two breaks is the same. So it's the same technique here. We use homeomorphism, okay, because it's a set living in R2 cross the time interval 0 to 1. So we still consider the homeomorphism. Okay, family of homeomorphism, okay, that can map one break to the other break. Basically, if you plot out this homeomorphism, right, it would be a movie. Okay, movie going from one break to the other break. Okay, it will be a movie going from one break to the other break. Okay. So the theorem is, if you consider all these equivalent classes of break on n strand, actually you can write down this group presentation here. So how do you view break as a group? So basically you just stack one break on the other. Okay, you stack one break on the other. So for example, let me draw some picture for you. So maybe you can stack two break together like that. So I mean, maybe some of you will come from my abstract algebra class, right? So if you are coming from my abstract algebra class, what we did was there's no twist here. Instead, we just consider the crossing. Okay, but in break group, we consider the twisting. So if you twist, under twist or over twist will be different. Right. So if you know more about group presentation here, okay, so let's look closer to that relation here. So sigma I and sigma j commute. Okay, when I and j is far, and sigma I plus 1 sigma I is equal to sigma I plus 1 sigma I plus 1. Okay, so they how to say these two are the break move. Okay, for the generators. Okay, so these are the specific generators that we picked for our break group here. So actually, there's a natural map from break group to symmetric group. Let me think. I think it's the other way around. I think yeah, do something. Yeah. Yeah, I think I do something wrong. So there's a map from Sn to Bn. Okay. Because Sn, there's just one more relation than Bn. Because Xi composed, right? But Bn also. Let me think. Is it the right way of?
Yeah, absolutely. Yeah.
Bn back to Sn?
No, Bn is
Yeah.
great.
Oh, right. Sure. It's a quotient. Correct. Thank you. Right. So this proves that you guys are not sleeping. Okay, good. So it basically, yeah, right. So if we quotient out this relation here, actually they are isomorphic. Okay, so if you quotient out this relation here, they are isomorphic. Okay, good. Thank you. Good. So let's continue. So similarly, you can define projection for break diagram for break. Okay, it's the same story. And you can prove these kind of equivalences. So when are two break in R3, I mean almost R3 to be equivalents, you just consider these three break move here. You have seen type 1 and type 3 before in the randomizer move, right? Okay, because type 1 is just putting two strings together and put it away. And type 3 is the same. You can bring a string across a crossing. Type 2 is a bit different. where you can move the crossing up, down the string. Okay. Sorry?
Identity times switch equals to switch times identity.
So let me write down the algebraic here. So algebraic expression here. So for example, the first one will correspond to sigma I inverse equals to the identity. And then the other side will be sigma I inverse sigma I. And then the next one will be, let's say, we're doing sigma I first and then do identity equals to the identity doing sigma I. So we're seeing the break from bottom to top. Okay, bottom to top. So we are composing break here. And then the last one actually is the break move. Sigma I plus 1. And then you twist sigma I again. And then you twist sigma I plus 1. Sigma I plus 1. So actually these are the group property of these geometries. Okay, basically. So in this case here, we'll abuse notation. We just use sigma for every break. You want to think it as a geometric break, or you want to think it as a break diagram, or as abstract break, it's fine. Okay, we just consider. So then in that case here, what does it mean by a closure of a break? So you start with a closure. Okay, sorry, you start with a break, and then how do you take the closure? You just identify the upper end and the lower end. Okay, of this string. Then you will form a link. Okay, then you form a link. So in this case here, how many S1 do you see? Actually, you see 1, 2, 3, 3 S1 here. Then 3 S1. Okay. Let's continue. So what can you observe from here is every break will give rise to a link. So every break will give rise to a link. Okay, using this break closure property. But you want to think the converse is true or not. If I gave you a link, can you find a break? Okay, such that if you close it, it is the link. Okay. Yes, you think yes. Okay. Actually, we need an extra condition here. Okay, we need to orient our link first. A link is oriented if each of its embedded x1 is oriented. So you can imagine that if you are given an x1, okay, there are two ways to orient it. So either you can orient it anti-clockwise or clockwise. Yeah, exactly, this is what we did in calculus 2 just now, right? Okay, yeah. Same sorry need to draw the other way around. Okay, clockwise and anti-clockwise. Thank you. Okay. So once we have this orientation, then every oriented link arises as the closure of a break. Because you need to think about our break. Our break has natural orientation there. It's top to bottom, bottom to top. So there's already a natural orientation there. Okay. So how about relating oriented links to the break diagram? So this is by a Markov theorem. So there's an equivalence between oriented link and break diagrams here. But in this case here, not just a break move can help you to identify this. You need extra move here, which is called the Markov move. Okay, so which is called the Markov move here. So what's the Markov move here? So first, you require the break to commute. Actually, in principle, in break group, it is not abelian. Let's say they won't commute. But in Markov move here, we require them to be identified because you need to understand that we need to take closure. Okay, once you take closure around this move, you can move the break top and bottom and across. Okay, so this is why it works. And the second type is you can introduce an extra crossing here. Okay, why it works? Imagine you can close it again. Okay, you imagine you close it again. Then you can simply untwist the middle circle here. Okay, to make it trivial. Okay, so you can recover the original closure. So similarly, we will have an oriented randomizer move also. So you can prove these equivalence. Okay, for oriented links. So it turns out that oriented links is pretty important. And the link invariant we're going to give, which is called John's polynomial, will be defined on the oriented links. So meaning if you have a links with different orientation, they should give you different jobs only. So orientation is important in this case. So the upshot was to study oriented links is just to study break. So we have turned a topology problem to an algebra problem. Okay, yeah.
So in the link, you have several S1, and each of the S1 should give the orientation, can be given orientation independently, and
Yes.
they will become different brands.
Yes, they correspond to different bread to give the yes. Okay. Yeah, so the detail is in the proof of Alexander. Alexander. Okay, Alexander. Yeah. So how do you do it? It's in the proof. Right. So let's go to the. We have half more hour. So let's go to the third section here. So faithful representation of bread group. So the slogan here is linear algebra is the best. Okay. So better learn your linear algebra well. So linear algebra is the best. So in 2001, Covano-Seidel defined a faithful representation of bread group, okay, on the bounded homotopy category of some module over algebra called AN-1, okay, zigzag algebra. And simultaneously, they define on the topological side, they have a faithful representation of Bn. On the infinite cyclet side, a cover of n-punctured disk, which we won't discuss how we define it, but I'll tell you some insight that we need from this construction here. So basically, if you write down the map, how should it look like? So first of all, we have a representation, okay, from Bn to where? To the, let's say, the endomorphism of this category here. Okay, later I will introduce, define this category for you. Don't worry. And on the other side, we have a topological action from Bn to this Dn. Okay, so how do we understand this Dn here? So we should send it to the diffeomorphism of this here. So on one side, we consider homomorphism, okay, endomorphism because of homomorphism between the sense space. On the other side, we consider the diffeomorphism. Okay, basically these are the differentiable map. Okay, the same space here, Dn tilde. So Dn tilde, if you are worry about that infinite cyclic cycle, for the moment you can think about n-punctured disk first. So what's an n-punctured disk? So basically you take a disk and then you puncture it. Okay, you have n-punctured there. Pick up n. Okay, and then we will look at some covering space, infinite covering space of this space. Okay, right. So no worries. We will see some concrete maths in a moment. I'll show you some concrete maths in a moment. So first of all, let's define what is a zigzag algebra here. So this is a very common rhetoric tools, okay, which is a quiver. So what's a quiver? Quiver, to specify a quiver, you need to tell me a set of vertices and edges, okay. So basically, if I want to define this n-1 quiver, we have n-1 vertices. And between these vertices, we put two arrows coming back and forth. And then we have a name for these arrow and this dot here. So if we're going from 1 to 2, we'll call it a path from 1 to 2. Similarly, we have a path from 2 to 1. And at each vertices here, these are called a constant path. Okay, so you are not moving, you are staying in the vertices. Okay, so basically, what is the algebra here? So in the algebra, there's two operations. You can plus, you can multiply. So how do you multiply here? So actually, this is what called the path algebra. Okay, so meaning you just concatenate path. Okay, if you can concatenate, for example, 1, 2, 2, 3, you can concatenate, you will get a path from 1 to 3. Okay, if you cannot concatenate, because their endpoint and starting point is different, for example, 1, 2, and 3, 4, then they compose to 0. Okay, so it's quite intuitive here. So we consider the path algebra, but we quotient out some relation here. So what's the relation we quotient out? First of all, we cut out all the length tree path. Okay, so we cut out all the length tree path here. So let me write down the general formula first. And I'll tell you one example. For example, 1, 2, 3 will be 0. So we cut out length tree path. By this, we will cut out length tree path. And the other one is we identify the loops. So identify I plus 1, I to be I minus 1, I. So in picture, what does this mean? So this just means that if you go around, if you go from 2 to 1 and then come back to 2, it's the same as you go from 2 to 3 and then 3 back. So what we call about this loop is what we call X. SI is this loop here. So for notation convenience, we introduce this XI. Right. So what's these two objects here? So what are the objects that we're interested in these two spaces? Okay, I need to tell you. So on the algebra side is a category. So in category, I should tell you two main things here. So one is object, the other is morphism. And on this, then we are interested on some curves. So what are the curves that we are interested in? So in the category, what we have is called the bounded chain complexes up to homotopy equivalence here. So to talk about chain complexes, right, I need to tell you what the chain group is. Okay. So the chain group we're going to use here is called projective modules. Or rather, we can take direct sum of projective modules here. We call it PI, okay? And there's a grading on it. We can grade it, okay, for the purpose of morphism. It's not important now. And then what's this PI here? So basically, PI here is a Z-graded path ending at the I vertexes, okay? So for example, what can exist inside this module here? So what can exist inside this module here? For example, I minus 1 I, okay? Or you can do I plus 1 I. Or you can take the loop around Xi. Okay, basically these are the elements there. Yeah, because due to our zigzag algebra, the longer path we already eliminated. Right. How about differential? Okay, to talk about chain complexes, you need to know about differentials also. Okay, so what's the map between PIs? So if you go from PI to PI, there are two maps. So one is the identity maps, the other is the XI maps. Okay, XI maps is the loop map, identity is just the usual identity. And then if you go from I to I plus 1, there's an obvious map you can put, which is the path from I to I plus 1. And then basically that's all. Also make sure that when you put these chain group together, when you compose this differential, it should satisfy DD equals to 0. Okay, so this is what you did in algebraic topology. Okay. Right. How about on topological side? So let's bring out 4 punctured discs here. And what we're interested is curve with endpoint in 2 different punctured. So for example, this guy here. Okay. A curve with endpoint in 2 punctured. Then I want to tell you how to connect between these 2 spaces. So if you have a curve inside this DN here, what you can do is you can put orientation on your curve. Okay, you can put orientation on your curve. So how to prove orientation on your curve? One, you surround a punctured, you will put a clockwise direction. Okay, you can put a clockwise orientation. So if you look at this bit here, it is going over the punctured 2, then you will put a clockwise orientation here. And then on the other side, if you go around the punctured 3, you also put a clockwise orientation. Okay, so how does this orientation play out? So how to go from this curve to this algebra here? So basically, you draw a vertical line between these vertices. Okay, you draw a vertical line between these vertexes, and then you name it in sequence 1, 2, 3, for example. And you look at the intersection between vertical line and the curve. Okay, so in this case here, there are 3 intersections. Okay, so these intersections will correspond to 3 modules here. So how to get the 3 modules here? So based on your intersection with this vertical line, for example, this one is related to 1, P1. This is related to 2, P2. The other one is related to P3. Okay, so there are 3 modules, 3 chain groups you need to put together. But how to put together these 3 chain groups here? So look at the direction of this curve. Okay, so you can see that if I follow the direction of this curve, I should attach a map from P1 to P2. And similarly, I should attach a map from P3 to P2. So this is how I construct these chain complexes. And if I draw you another example here, okay, you can see that there are also 3 intersections here correspond to P2, P1, P1. And you can see that there's a map from P2 to P1, and then P1 to P1 again. But what's this map here? This is what we associate as a loop map here. Okay, because you already go 1 round. Okay, loop map. Okay, so when we attach the loop map here, we decrease by a degree to record our map, what happens to. And then on the other side, sorry to mention about the morphism in our category, it's just chain map. Okay, chain map using the differential map. So, yes. Yes, these are the differential. Sorry. So, do you want to ask why these compose to 0? Sorry, which one? Part B. Yeah, part B. Yeah. Yeah, these are the differential map. Yes. But you won't see identity attached with all the other maps. This is impossible based on our construction on our curve. So you won't see like identity. These are not the chain complexes that we are interested in. So we won't have this kind of problem. Because usually identity and your identity don't compose to 0, right? So, but we are not interested in this kind of chain. So we only consider chain that is really define a chain complex. Yeah. Any other question? Well, I mean, yeah. So maybe if you are confused, because we only consider the chain complexes up to homotopy equivalence. So if you have a PI identity between PI, this is homotopy equivalence to a 0 complex. So it will be cancelled out. Well, I mean, write this. So this is equivalent to the 0 complex. Because we only consider chain complexes up to homotopy equivalence. Okay. Right. So a theorem is there's a one-to-one correspondence between these 2 spaces. Okay, we'll see soon where is it. So, well, I need to define the break operators. So I need to tell you how this break group elements add on these chain complexes. So actually we need to define another chain complexes, but in this case, this is a bimodule complexes. Okay, bimodule complexes. So this is a bimodule complexes where we have the PI just now, okay, which is the left module. Now we introduce a right module IP. So what's IP here? So PI is the path that end with I. Then IP will be the path that start with I. So this is the construction here. So you should check that these actually satisfy the break relations. Okay, all the break moves. Right. So if I want to tell you about calculation, right? So I need to tell you how this right module and left module compose. I mean, tensor together. Okay. So if you tensor with different J, you get a different Z module. So for example, in these 2 cases here, if you consider a path from I to I plus 1 or I minus 1, what could it be? What is a path that start with I and I plus 1? So in our case, it's really just I to I plus 1 or I minus 1. Yeah, because we cut out longer path already. And then what about further j? Okay, further j than 1. It should be 0 because by the type zigzag algebra, we cut all these long path away. And last case to consider is when j equals to I. Okay, so how do you start from an I vertex and then back to an I vertex? Either you stay there or you make a loop around it. So it is a two-dimensional Z. And then we put a grading here to acknowledge we have a different basis. Right. So last thing I need to tell you is this topological action here. So how sigma I add on this is simple. It's like symmetric group. You permute. You permute. Okay, you just permute function. But professional word here is about then twist. So you need to tell us if you permute the puncture, what happened to the surrounding. So I will show you some examples here. So let's look at one example here. Let's take, in this case, we'll take sigma 1 add on this time complex P2 here. What happened to during this tensor product? So you take the con of this tensor product of these two chain complexes. And using the theorem just now, 1P cross P2 will reduce to a Z module. But we are tensor over Z. Okay, so this is really just P1. So you make P2 a bit longer. Okay, P2 become P1 to P2. But on the topological side, what happens? So how do we associate P2? Do you still remember? Okay, so there's only one intersection P2, right? So this corresponds to the second, in this case, the second vertical line intersect with your curve, which is this curve connecting 2 and 3. But if you're going to permute, what is sigma 1? Sigma 1 is permuting the vertex 1 and 2. So if you permute it in the anti-clockwise way, what happened? The curve also get longer. Okay, so when we permute, we don't move. So we make an annulus around these 2 points, and then we only permute things inside this annulus. So you can see that the curve get elongated. If you really do the algebra again, so maybe you want to test someone is listening or not. So we have this curve, right? Surround around 2. So how should I give these orientation? Anti-clockwise or clockwise? Clockwise, right? Clockwise. So we do this clockwise here, and then we do the intersection again. So there are 2 chain group corresponding to this intersections, and there's a map from P1 to P2. Okay, so they really correspond to each other. Okay, one we do algebra calculation, the other we do a topological calculation. Okay, so they coincide. So what you can prove is there's an equivalence of representation of break group between these 2 spaces. Okay, they are actually an equivalence of representation. You can either add and then go to the topological side, or you can go to the topological side first and then add by a break group. That should give you the same answer. Okay, so this is quite a strong statement here to go, because you need to go through all the possible topological cases considered. Okay. So, right. We started late, right? I think I should have at least 10 minutes. Right, so on the other hand, we can consider homomorphism between 2 chain complexes, okay? Or we can consider an intersection between 2 curves. Maybe talk about an intersection between 2 curves first. So let's start with this. Okay, and then if you look at 2 different curves, you can actually look at the intersection number here. So in this case, it's easy. These 2 curves intersect with 1 point. Okay. But when we consider an infinite cyclic cover of this space, we can break this point. grade this intersection. And on the other side, correspond to this picture here, we also can consider the home space between, let's say, P1 to P2, and this case we have P2 to P3. So consider what's the home space of this. So it should be a Z module also. It should be a Z. So the surprising result is, if you consider the point correct polynomial of these two chain complexes, it is actually equal to the bigraded intersection number. So what does it mean by point correct polynomial here? So basically, you take the two chain complexes and you can shift it in the cohomological degree, and then you calculate all the possible home space there. And this should be equivalent to this bigraded intersection number. Okay. So you consider all possible shift of your chain complexes, and then you look at the home space. I mean, maybe you think that, oh, you can shift in the Z direction, it's infinite. But if you look at this case here, you can't really shift far. Okay, so how many ways you can see? So maybe you need to consider, is there a map between this shift? Okay, or you can consider whether you have a map in a different shift. So let me this a bit. Or you shift the other one in another cohomological grading. So maybe shift P2 to P3 across. So is there a chain map like this? Or if you shift it really far away, there's only left with a zero map. Okay, so there's not too much you can do, because what we care about here is a bounded chain complex. So bounded chain complex means for large cohomological grading, it should be zero. Okay, so we only care about bounded chain complex. So this module here is also finite dimension. So how about the faithfulness result here? So actually, to prove a faithful representation here, actually we will relies on the topological argument. So if you look at a two curve intersection in the disk, okay, what happens is, if it happens to be equal, okay, to another intersection after you add by the break, okay, and similarly it is equals to adding the break twice, it is identity, then this proves that your topological action is faithful. Right. So faithful idea means what? What does it mean by a faithful group action? It means that there's only identity element that acts as an identity. You don't want non-trivial elements to act like an identity. Okay, so if you use this intersection number here, it will trace whether you will send a curve to something else or not. Sorry? Yes, injective homomorphism from the group to the permutation of the object. Yeah, right, injective, yes. So in this case here, we use this intersection number to trace it. Okay. In case that this sigma is not identity, meaning that you will have a non-trivial break that give you the same intersection, then this is not good. So the corollary is the algebraic action is also faithful. Use the equivalence of representation we had just now. Yeah, it turns out that topological one is easier to, so we'll use it. So okay, come to the main dish now. So what's the categorification instance here? So one thing you can see from the point correct polynomial was, if you compute the dimension of your home space, graded dimension is the intersection number there. But you can see that this home space here is some vector spaces. But what's this integration number here? These are natural number that's graded. Okay, so these are the graded intersection number. Okay, so you can see that there's some positivity here that we can refer to. Okay, so we attach vector spaces on these number. And what else? If you provide a proper grading, we can see that actually these break, let's see, this is a algebraic action here, also categorify a classical Bourgeois representation, if you know about it. If you don't know about it, it's defined. But if you know about it, how you recover this Bourgeois representation, it is by after taking the, if you take the action of this sigma I on this simple module, I mean projective module, Pi, P2, P3, P4, for example, in this entry cases. And then after you take the Euler characteristic, then you will get this matrix. So that's why I mentioned about linear algebra at first. So once you reduce the structure, it is just a linear algebra. But actually, there's a more sophisticated structure here, which we call the triangulated category. So triangulated category is much related to linear algebra. Okay. But in this case here, we have more structure here. This matrix has a coefficient in Z. Then we have negative now. Previously, it's just positive stuff. Now we can have negative stuff. Because this Euler characteristic will introduce a alternating sign, if you remember. Right? The faces, what's the formula for the easy graph? Face minus. Yeah, so there's an alternating sign here. But we are considering a more general Euler characteristic. Right. So another problem is if you collect all these are just now the theorem that I told you, right? What is 1P1, 1P2, 1P3? If you collect this Hom space here, you can see this matrix of modules. But if you take graded modules, it reduces to some coefficient, I mean polynomial in Q. And if you substitute Q as -1, what do you see here? Actually, if you know much about combinatorics, this is a type A kappa matrix. If you know about Lie algebra, so this is a type A kappa matrix. Or if you are a geometric person, this is actually a negative of type A intersection form. Okay, so these are not coincident. Okay, so these are purposely built for the structure of this. So what did I do? My work with Edmund, so he's in France now in IHES. So my work with him was to extend the above, what we mentioned just now, the story to type P quiver. So what's the type P? What's the difference here? The type A quiver will have three label on all the edges, but here we have an extra 4 here. So what we do is we replace the homomorphism in this region here to a 2-dimension. And then we work out the algebra. Right. So mentioning about the intersection form here, so I want to talk about this guy here. So if you look at the Hom space of Pi, Pj, so the tensor product between IPJ, it is actually the Hom space between exceptional divisor also. Okay, well, so where do you get the divisor from? This is coming from the type A Müller fiber. Okay, so if you consider this Müller fiber here, and then you do the blow up thingy, and then you can see that they intersect at 1. Okay, and then if you take the dual picture, it's exactly the type A quiver I just. Okay, so this is the algebra geometric story here. Second, on the symplectic side, what Seidel did was it defined a bunch of Lagrangian sphere. So these are the Lagrangian submanifolds, so they are half dimension of the original space. So this M is exactly the Müller fiber just now, but they can put a symplectic form of it on it, so it becomes a symplectic manifold. So in this language here, the Hom space will become the Fukaya algebra of the Lagrangian sphere. Okay, become a Fukaya algebra. So there's a A infinity structure here, if you like. So there's a A infinity category involving, but a very simple case one. So one possible question is I asked to my FYP. So I mean, maybe it's a hard question to ask. Obviously, they start with a basic first. So what is the geometry that I get if we use a type B quiver here? Okay, so what kind of sphere we can get here? Okay. We already have a story of a topology story, algebraic story. So do we have a geometry story on it? Can we extend it to this Mueller fiber case on it? Do it? What's the space we're looking for? Actually, if you see here, there's a deeper theme going on here, which we call the homological mirror symmetry. So basically, we have algebra, and then on one side we have algebraic geometry, on the other side we have symplectic geometry. So we use algebra to link these two spaces. So we look at the home space between some exceptional objects. Algebra. Right. How many times do I have? Few minutes. Okay. 5 minutes. I'll finish it.
Maximum.
Maximum. Yes. Thank you. So last is okay, not last. Okay, almost last. So do we get a categorified link invariant? In this case, the short answer is no. Okay, we don't get a categorified link invariant here, although we have a break group action here. We do categorify a temporarily algebra, but a new categorifications. So you can see what happens here is ui uj equals to 0. But in the proper link invariant case, Jones used these temporarily algebra coming from the polynomial algebras here. They look at this algebra that satisfy all the other relation that we categorified with this EI, EJ equals to EJ, EI. In our case, why they are equal? Because both of them equal 0. But this is exact, I mean, it's not equal because they are trivial. Okay, there's some other structure inside here. And with this, Jones defined a Jones polynomial, okay, using some representation using the representation from break group to temporarily algebra. After taking trace. Right. So there is a successful case. So at the categorical level, a Kovanov homology has successfully categorified Jones polynomial. And it is proven to detect unknown. So meaning what? Meaning if you have the same, if your knot have the same Kovanov homology with the unknown, but Jones polynomial, not sure. If you have the same Jones polynomial with unknown, it's not sure that whether you are unknown. It's not proven. It's not given counterexample. Okay, both is unanswered. Okay, so there's some room to work there, right? But at the categorical level, it's proven. Okay, once you have the same Kovanov homology with the unknown, then you are an. Yeah. So it might seem that topology is easier to work with, but actually this higher structure or more abstract maps can prove stuff easier than what you can work on. So last, so the future word was we try to replace this homotopy category here with a two category. This algebra here is a Reeve product of a n with Sn. So basically you look at n of an here, and this corresponds to taking all the possible curve you can take inside 100 this. And why we look at this? Actually, there's a conjectural break group action conjecture by my supervisor, Tony Licata. Because if you look at this Reeve product space here, it is actually a Fock space, okay, which is a representation of Heisenberg algebra. And this Fock space actually is quite interesting. It is related to cohomology of Hilbert Steves and Nakajima varieties. And it's proven that there are Heisenberg algebra action on these spaces. So hopefully in future we can look more into this. So before we end, last one. So I want to end with an excerpt from this Chinese poem here. So this is a Wen Tianxiang coming from Wen Tianxiang, 正气歌. So first line it says that 天地有正气，杂然复流行. So as a categorification mathematician, I will translate it to in the universe there's positivity and varieties give rises to metaphor. So linking all the ideas together.
Okay, thank you. Okay, creative translation. All right. Maybe you have time for like one quick question. A quick question, anyone?
Oh, good question.
Yeah.
You know,
Okay. Yeah, Lagrangian or
Yes.
this one?
yeah.
Okay, this one.
Theory?
Sure, it's related to singularity, but the way we introduce the type B algebra is using some Z2 action. So hopefully we try to figure out what kind of a Z2 action is makes sense to define this Lagrangian sphere. Yeah. So well, I mean, okay, sure, okay. So in the old classical types by Arnold, they also studied type B singularity. Yeah, type B singularity. So I suspect there's some connection there. But this kind of construction of Lagrangian sphere is really modern. Although it uses, I can see that the idea is coming from Arnold, but this construction is really modern by Seidel. Yes, by Seidel. And it's not really. This one is just Seidel. This is quite early work by Seidel. So Seidel and Kovanov worked together, and then Seidel defined this. I think Seidel first defined this kind of thing, and then he worked with Kovanov with this break group. I think this was when he was a student or maybe just graduated, because the paper from Kovanov and Seidel actually came from the idea of Simon Donaldson. So it's a Seidel supervisor. So they defined this Lagrangian sphere. Turns out that this intersection has the same configuration as the quiver. Right. So I mean, I try to link it to the Müller fiber of type B singularity, perhaps. Also, the other way is to look at it is to introduce a Z2 action on the type A singularity, and they should have a relation between these two, because in our paper we actually relate the type A and type B story together. So we can go.
Okay, thank you, Kiseng. Thank you all for coming. Let's give him a round of applause. We're taking a break from seminars until what, December. We have yeah. We have one last seminar on December 22nd. December what?
No.
6th December. Okay. We're taking a break for the midterms, and then we'll have a 6th December talk. Yes, Darshan? Yeah, talk to Munir about the scheduling.
29, I think.
Yeah. Oh yes, 29. We have the main campus joint seminar. Okay. Right. Thank you, everyone. Right. Bye. Okay, so I'll ask China for the recording.
Okay, sure.
Yeah.
Thank you. Okay, thank you for coming.
Yeah, so my account was WeChat, like because the Gmail was WeChat.
Oh, I see. Okay. So